Okay, we're moving from similar triangles now into trigonometry in this unit. So we just need to revisit some of the properties of similar right triangles so that we can get a baseline for how trigonometry is going to develop and how it's going to be used. So if you take a look at exercise 1 here, we're trying to justify that these triangles are similar. And as you look at their side lengths, if we take the longest side in each triangle and divide them, so 10 divided by 5, and then the middle side, 8 divided by 4, and the shortest side, 6 divided by 3, we end up with the same scale factor every time. So if the scale factor is consistent, we say that we have side-side-side similarity, and so these two triangles would be considered similar. So in part B, it's asking us to determine the values of the following ratios, and all of these ratios are within the same triangle. So for BC over AB, if I just take those two sides, I have 3/4, and BC over AC is 3/5, and AB over AC is 4/5. So all we're doing here is establishing a ratio between two sides within the same triangle. Now, if I convert those to the other triangle and do their corresponding segments, so EF corresponds to BC and DE corresponds to AB. So basically what I'm doing is taking the large triangle's version of BC over AB. Checking its measurements, turns out that that ratio is also 3:4. EF over DF does the same thing, divides out to 3:5, and DE over DF does the same thing as well as its counterpart and divides out to 4/5. So what we're seeing here is that the ratio of the corresponding sides is not only equivalent between the two triangles, but also within the triangles themselves. So all of those relatively positioned sides are going to end up having the same ratio when the triangle is similar and dilates out or dilates in. All right, so that's going to be a key notion throughout this unit. Okay, exercise 2. DEF is a dilation of ABC by scale factor. Algebraically prove that DE over EF is equal to AB over BC. Well, if I apply a scale factor to AB and BC, and then I apply the same scale factor to, if I apply the same scale factor in the numerator and the denominator of AB over BC, as you can see here, what that's showing is that I'm essentially multiplying it by 1, and so DF on the left side is equivalent to AB over BC on the right side because the same scale factor has been applied on the top and the bottom. So that's just showing that if I scale up both sides the same way, I'm going to end up with the same ratio. Okay, exercise 3. So we know that we have some more triangles here, and we can draw those and put the labels in as given. Which of the following is the ratio of EG to EF? Well, in order to know that on an unlabeled triangle with no information given, I just want to find out what segments EG and EF correspond to, because I know that that ratio is going to be the same as its similar triangle counterpart. So EG is in that 1 and 3 position in its name. So if I take the first triangle, that would be MP. So that's talking about the 14 segment. And EF is in the first and second positions. So EF would correspond to MN. And so that would have to do with the 10. So if I take 14 and 10, that's the same as taking EG and EF. So 14 over 10 reduces to 7/5, and that's my ratio. So I just talked through that as if there was no illustration. You can certainly draw the illustration, and then however you label your first triangle MNP, you'd want to make sure the second triangle gets labeled the same way. So as long as you match it up, the illustration may help. Okay, on to the next page. So these ratios come into play with several kinds of problems that we can use to solve them. A person in exercise 4, person 68 inches tall, casts a shadow 54 inches long. This is a classic style of similar triangles problem. So assuming that the sun is at the same angle, if that same angled sun casts a shadow from a tree of an unknown height and we can measure the shadow, we can use scale factor to figure this out too. So in order to solve this, we can set up one fraction that shows the ratio between the person's height and his shadow, and set that equal to a fraction that shows the tree's height and its shadow. All right, so you may have this drawn for you, you may not on a given problem. So you may have to draw this yourself. I certainly would not get into the detail of this illustration, but we do need to see those two triangles so that we can figure out what goes with what. So h over 18, 68 over 54 represents those height over base, if you will, on each triangle. And then we just do a cross product and figure out what it comes out to the nearest foot. Another way you could have done this is to take height over height and base over base. That would work too, but what we're trying to get into the habit of here, or at least be proficient doing, is making a ratio within the same triangle. So that's why we see 68 over 54 and h over 18. And the only reason this works in this case is because we're assuming that both the person and the tree make a right angle, and we're also assuming that the sun is making the same angle because it does say at the same moment. All right, exercise 5. A rectangular picture has a width of 4.5 and a height of 3, so that's drawn over here. If the picture is to be scaled such that the new width is 6, what is its new height? And what is the length of the diagonal? Well, again, if I have similar figures, then the ratio between sides should be the same. So this is saying that it's going to be scaled, which indicates that it's been enlarged proportionally. So the ratio between the two, the height and the base of the original rectangle, should be maintained in the second rectangle. So 3 over 4.5 makes one fraction, h over 6 makes the second fraction, and we can solve for the height. And once I have any two sides of a right triangle, I can find the third one just using Pythagorean theorem. So getting that last bit is a matter of using the 4 and the 6 in Pythag. Okay, exercise 6. One of the classic engineering uses for similarity is measuring the width of a river. And this kind of problem tends to come up in textbooks quite often. So it's not being that it's not easy to measure the width of a river or any other kind of body of water, what they do is put 2 points on opposite sides of the river, call them A and B in this diagram, and then they measure a distance along the side of the river to another point, we'll call it D here, and then walk away from the river a certain distance and figure out what that line back to the original point would be. Okay, so if you can sort of figure out what's going on in this diagram, if I'm standing at point A on the side of the river, I can walk to D and I can walk to E because that's all on land and measure how far I went. So explain why this triangles must be similar. Well, both of these have a right angle. This one makes a right angle with the river's edge. This one makes a right angle with the river's edge going the other way. They also have that vertical angle pair, and so the two triangles would be similar. Why that's useful is because if I know the distance that I walked and I can figure out all of those walking distances, I can then apply it to this distance at where the river exists. So if I know how far I went to point C, and I know how far I went to point D, and then out to point E, I can use those 3 segments to figure out what AB is. Okay, so first off, the distance to C would be the total distance 225 minus the secondary distance 30. So I have 195 for that. I know that the AB and the BC segments will form a ratio because they're in the same triangle. DE and CD would have the same proportion or the same ratio as AB and BC because they correspond in the second triangle. So I just want to put in all the information I know. I know that BC is 195, DE is 12, CD is 30, and so I can do a cross product and solve that and get 78. So you'll see several problems like this, similarity problems that will allow you to get missing sides on triangles by setting up ratios and making sure that they match up.